Hi. In the last video, I was able to wrap up, or very nearly wrap up, the control ROM control logic and one of the control ROM modules itself. I'm able to emulate that and perform the copy from EEPROM to SRAM. It's not quite perfect yet. I do have a few things I do need to clean up, and I'm going to start with that in this video. But I am going to clean up the schematic, and I am going to break out a breadboard and start putting it on breadboard in this video. Let's get right into that.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
Okay, let's start by addressing the biggest problem. The 74 HCLSXX, whatever you want to use, the 03 is not an AND gate. It is, in fact, a NAND gate. And this means then that my design is flawed, my emulator is flawed, my implementation of that IC is flawed, and all of that needs to get cleaned up. So I'm going to jump in and start with the block diagram and straighten that out first. Once that's addressed, I'm going to go to the emulator code and address the issues with the 74XX03 class. And then I'm going to make the changes to the control ROM control circuit so that it is properly wired up, given the fact that this is a NAND gate, not an AND gate. Okay, now I don't have anything actually outputting directly off that control ROM control for the reset hold, so I'm going to call that good, at least for now. Okay, next up I've got some optimizations I believe that I can make. And to do this, I'm going to start by looking at OR gate 1 here. Now I have gone through in between videos and made sure that the comments match the way that things are wired up. And I've got here on the page a printed copy of what I've got here, other than the last change that I just made. And the first one I want to look at is this signal here, the OR of not QS, not QC. So if I take a look at a truth table here, I have 0, 0, 0, 1, 1, 0, 1, 1, and then my Q result, not S, which is inverted, which would make that a 1, or not QC, which would invert that, would make that a 1. This would also be a 1, this would also be a 1, and that's a 0. Well, that very easily turns into a NAND, and so I can take this signal and move it up here to one of these NAND gates that's not being used. So I could set gate 3. Well, let me use my notation. NAND 2.3 would then become QS NAND QC. And the proper way to write this would be QS QC, like that. That gives me the ability to take this signal here and move it down to this unused gate and this OR gate. And ultimately, that allows me to eliminate this whole IC OR 1. I'm going to make those changes real quick. The next step here is to run through this once all the way through and make sure that everything is still working after those changes. And once I have confirmation of that, I will rename OR 2 to be OR 1, since I don't have two OR gates anymore. Very good. Okay, the next signal I want to look at is down here on the inverter. So I am inverting the result of not QS or not QC. And again, if I write up a truth table for that, my Q output, if I invert QS, invert QC, so 1 or 1 is going to be 1, but I invert the output of that, that's 0. 0 or 1 is 1, invert the output of that is 0. Same here is 0 and 1. Well, this is an AND gate, and I just so happen to have 3 unused AND gates up here. So this could be QS and QC. So let me make this change when I do, this reset is just a simple inversion. I still have NAND to gate 4, which should be reset, NAND, reset, which is a trivial replacement of an inverter, and that allows this second inverter to go away. Let me make those changes. And once again, I'm going to compile and let this run all the way through just to make sure that I didn't break anything and I get a good sanity check at the end. Very good. Okay, for the schematic, the best thing to do is to go through and just double check every single connection and make sure that every one of them are exactly as they're supposed to be. There's enough change in here that I could justify gutting the entire thing and starting over. There are risks, at least for me, in using this as a starting point. I may end up missing something. But for the moment, I'm going to go forward with this and let's see what happens. I'm going to likely go through and check this several times before this video is over. Okay, there's a lot of fussiness in here, and I don't necessarily go through this in the most efficient manner. I have a lot of rework that I end up doing. So I'm just going to jump ahead here a little bit and get to some more of the relevant commentary. It's right about here that I give up trying to go through the code pedantically and instead just make sure that I get everything wired up in the intent to go back through a second time and validate everything. Okay, at this point, I have basically all the glue logic sorted. Well, I believe I have all the glue logic sorted. And what I want to do now is I want to run an electrical rules check and just see if there's anything that I'm missing. And I do expect several things to pop here. So with that said, let me do that and let's figure out exactly where all the problems are before I go back through and double check and make sure every one of my connections are correct, because I know I'm missing some. It was this portion of the cleanup that actually took the most time and effort to accomplish. And the problem is I had signals named several different things, or at least not each signal was named uniquely. And so I had to come up with a method in order to get through all of these signals and have a single name associated with them, but still be able to track exactly what each one was. I did finally come up with a solution for that, and that was just to add some names next to the pins with conflicting names and ultimately remove the conflicts. Okay, I just verified this. NAND to gate 3, which is that gate there, is actually unused. So I'm going to move this down here into the unused portion of the schematic and give me a chance to connect this up. And that means that this can go away. All right, so the last thing then are the crystal oscillators, which are down here in the corner. And what I need to do is I need to figure out how I'm going to set that up properly, because ultimately I need a 14-pin cradle to be placed in there with only a few pins hooked up. Let me see what I can do about that so that I can get that cleaned up. And then I should be able to then walk through this one more time and make sure that I've got everything properly handled. And for the oscillators, I ended up creating a custom footprint, and then after that realized I needed a custom component and went ahead and made that, cleaned up any of the issues that I had as a result of that, and I will now have a place that I can drop either of the two form factors of crystals into this module. That looks better. Now, off camera, I'm going to go through this again and figure out what I might have messed up, but overall, I think I'm in much better shape now. I just have to double check my work, because knowing me and knowing what I normally end up making mistakes with, the risks are higher. Okay, and finally, it's time for some breadboards. Okay, so what have I done here? Well, I've managed to get the breadboards placed and hooked up with power and ground. All the ICs placed on here, again, hooked up with power and ground. All the decoupling capacitors hooked up, both the bulk on the power rail as well as the individuals for the ICs. I've placed a 10 megahertz crystal oscillator in here, and I know I'm about the limit of the breadboard here with this, but I definitely want to see if I can get this going a little bit faster than what it would be on the slow clock. So I'm going to make an effort to use this 10 megahertz crystal oscillator. I've got the inverter, I've got 3 AND gates, I've got the open drain AND gate. Up here I've got the OR gate that is going to check for all the bits for the bits counter, which is here. I've got the 4 address counter ICs. This is the shift out register. It doesn't have a whole lot of inputs, but it's got an output, so it's sitting over here. Up here I've got the D-type latch. I've got the 2 NAND gates for the 3 set reset latches, plus the inverter for the reset. And then I've got the 4 multiplexers in order to multiplex all 16 address lines between what's coming from the instruction register and what's being driven off of these address counters. Plus I've got, for the LEDs, I've got a line driver so that I can decouple that from the rest of the load. And then I've got the line drivers here that are associated with driving the actual lookup on the RAM module itself. There's no RAM module on this yet. Now I have mixed LS and HC technology, which means I'm going to need some pull-up resistors as I go through this. I've got some HC technology on order. Now it's supposed to show up later this week. Hopefully it will be here in time that I can actually replace the LS with HC and then just move on as if we've not missed a beat here. But other than that, I think we're good to start wiring it up. Now my plan is to get a better copy of the schematic and use the schematic itself directly as my wire up. If it doesn't work, there's going to be one of really 3 possibilities. Either the emulator and the hardware are not working congruent with each other. I made a mistake translating the emulator hookups into the schematic hookups, or I made a mistake translating the schematic hookups to the breadboard. Each one of these, we'll have to cross that bridge when we get to it. All right, let me pull out some hookup wires and we'll get going here. Okay, as far as where to start, I want to start looking at things that I can do to hook this up and take care of the shorter wires first, and manage to even get some new hookup wires. And I'm not going to go crazy here. So on the address multiplexers, here, there's an enable pin on pin 15 that needs to be tied to ground, and then my inputs on the most significant bit also need to be tied to ground. So those would be pin 14 and 13, as I'm trying to stare really hard at it to make sure that I'm looking at this right. So most significant bit is up here. 15 would be tied low. 14 would be tied low. And 13 would be tied low. Okay, let me pause there. I'll pull out the temporary hookup wires, get some more permanent ones put in there. And I'm just going to put my head down and plow through this. We've got a lot to hook up here for the hardwired high and low signals. Let me get it done. And it's right about at this point I realized that I have an error in the schematic. Recall that I had changed the bit counter to load a value of 9 rather than 8. I have that change in the code and I have confirmed that it's there, but yet I somehow managed to miss that in the schematic. Let me make a quick change here and I'll get back into the hardwired signals. Okay, as I'm going through the rest of this, it dawns on me that a good number of these connections are either going to be relatively trivial, as in connecting up line drivers to LEDs, or they are hardwired to ground or VCC. And I believe that's a good thing because ultimately what it does is it takes a number of the connections out of the mix and allows me to then focus on getting the more difficult, longer ones routed over the top of all of these. Anyway, with that, let me wrap this up and we will move on to some of the more difficult connections. Okay, I have started the process of adding this additional breadboard down here. And in order to do that, I wanted to move these ICs down so that I had landing zone up here for all of my interconnects. Make it a little bit easier to deal with that. Okay, this should then give me the place I need to bring in my signals and output my address bus. Okay, the next challenge becomes all of these longer signals. Now, it's a very dense board, and I get that. But if I start here in the upper left-hand corner, that IC, I should be able to take the input for each one of those pins, find out where it's coming from, and perform that hookup. In this case, I've got an internal reset signal. Oh, let me just put it on the screen. I've got an internal reset signal. I've got the reset signal itself, which is raw, which is coming up there. The internal reset signal just happens to be coming off of a NAND gate, and so I can pick up that NAND gate on the way. But that reset signal is also used here in the set reset latch. So if I look at this, if my reset signal comes in somewhere over in this area, I can bring it over here to pick up the set reset latch. The inverter is up here on NAND 2 gate 4, so I can easily come from there to there, but then I can jump from here over to, I think it was pin 4 that had the actual reset on it. And so what would be silly would be to come from this side all the way over here and then backtrack back this way. I kind of need to pay attention to where everything is going so I can pick it up from here, bring it over to here. I don't want to go to the top of the IC line and then back down to the bottom of the IC line. I'd rather go over here, bring it over to this IC, and then from this point bring it up here where I actually am going to have two connections because I have to tie both the A and B inputs together. All right, the last one I want to place is going to be this long line. So let me get these shorter ones taken care of. Okay, this is going to end up being just a lot of fuss like this, and if I bring you along connection by connection, this is going to end up taking forever. So let me get my head down, let me get into this, let me make some progress, and I'll come back and update you when I have something to update. Copying SR latch. Shifting SR latch. Latching SR latch. Select lines on the address multiplexers. Or 1. And make no mistake about it, this last gate was fussy. It didn't help I did it wrong twice. Bits counter. And to gate 4. We do the multiplexer select with the correct color hookup wires. Address counter, borrow, and carry. Address counter load lines. Address counter increment. And 1 gates 1 and 2, and 3 gate 1. Open drain NAND gate 1. Inverter 1, gate 1, and gates 2, 3, and 4. and one gate 4, and one gate 3, and 2 gate 1, and 2 gate 3, and 2 gate 2, inverter gate 6, and 5. Shift register. The final signal on the D-type latch. Okay, it's about this time I'm going to take a detour. I've received my HC logic, so I need to replace the LS in here with the HC, and I want to do that before I start routing more hookup wires over the top of the 157 multiplexers. I've got enough that I've got to sort through here. These LS ICs I'm going to let stay because they're only going to drive LEDs, and so I don't have to worry about mixing the logic there. The HC can drive the LS, which can drive the LEDs. Once I get that done, my goal is then to grab the multimeter and beep out each one of these inputs. There's only one output that can connect to any given input, so it should be relatively easy to go pin to pin and check each connection to make sure that they're good. Just an extra step after pulling up some of these hookup wires that are going over the top of the ICs, and to make sure I didn't make any silly mistakes to begin with. So I'll do all this off camera. I'll let you know if I find anything, and then come back to these multiplexers and getting those wired up. Okay, let me tell you what, beeping this out was absolutely worth it. It didn't take too long, and I found a few issues. The 3 connections here that are in green are ones that I actually missed, and so I actually had to go and make those connections, and of course in the process of making these connections I made a mistake that I then found when I checked, so that's a good thing. The ones here in pink were actually incorrect for one reason or another, and I had to go back and correct those. Some of them I rewired, but in the case of this OR gate here, I had them connected incorrectly. And so I just went back to the schematic and changed those so that the schematic matches. And I'll make the same change in the emulator so that the emulator and the schematic and the breadboard all match as far as those signals are concerned. All right. From here, then, let me get into wiring up the multiplexers here and getting the LEDs wired up. LEDs and flipping over the line drivers. The point of this is just to see if I can make all of these ground connections common, so then I can route the ground connection to the rail a little bit easier. Next, extend the counter ICs to the multiplexers and then continue that on to the jump point for off the board. It's C, D, and E, F is on U. 8, 9, A, and B. Multiplexer outputs to the LED drivers and off-board, F is unused. Bits 8, 9, A, and B. Bits 4, 5, 6, and 7. Bits 0, 1, 2, and 3. Okay, and once again, I'm going to make an effort to get through this rat's nest a little bit and see if I can't beep out these connections. It proved to be so useful last time. I want to make sure that I have the greatest chance of success when I apply power here. Okay, the last thing to tackle here is the instruction register input into the multiplexers. Normally I would leave these floating, but since I'm dealing with HC logic, I need to tie each of these low. I'm just going to use these temporary hookup wires for this. I will redo these connections with something a little bit more permanent once I get to that point. Let me knock these out really quick. Okay, it's been quite the battle to get to this point, but we are at this point, which is a good thing. There's only one input signal onto this module, and that is the reset signal. It is an active low, so I'm going to tie that high for the moment. And it's jumped around to a few places. This is just a convenient place to pick that up. ultimately it'll come over here to this section of the small breadboard over here. These instruction register inputs are going to land here, and they'll look very similar to these. Place your bets now. What are the chances I get this right? Certainly one of two things are going to happen. It's either going to work or it's not. Well, nothing to do but let her rip. Let's find out. Power. I'm not pulling too much amperage, but I'm not in reset, so let's reset this. It puts it in reset. There's some lights that aren't lit, and my oscillator does not appear to be running. These are no inputs into these. Okay, I forgot these signals, so you can ignore the blue LEDs here. Okay, let's get the logic analyzer out. So that is actually low and high and a low. No, that should be low. B should be low and it's high. This one is incorrect. C is on pin 10, should be high. D is on pin 9, that should be high, so that is incorrect. Pin 1 was supposed to be low, and pin 9 was supposed to be high. That's better. That looks correct. The most significant nibble was supposed to be pin 15 high. Pin 1 is floating. No, pin 1 is low. And that was supposed to be high. So the one thing I never actually toned out and double checked were my hardwired connections. And obviously I am paying for that. This looks promising. I don't know that it shows up on camera, but it looks like it's flashing. But that's now loading properly. Now, am I counting? So this shows, yeah, I am actually counting. This is incrementing. So that means that my input here I'm either going to need a slower clock here or I'm going to need an oscilloscope to figure this out. Running at 10 megahertz is probably creating some issues for me. Okay, here we go with a 1.8-ish megahertz crystal IC. This would be one that I would use in a serial UART, serial communications. So let me reset. So things are not going to count if you're clearing the counts instead of counting. Okay, I'm going to interrupt myself here. This is not a good change. It actually makes the situation worse. The problem is I'm looking at pin 15, thinking it's pin 14. So I'm actually making a mistake here, making the situation worse. Let me jump forward a little bit here. Let's start with the obvious stuff. This LED is on when it probably should be. And I certainly have a high signal coming into it, high signal there, high signal there. That is bit 9. So that should be the second bit up here, which is on pin 7, and that's low. Yeah, I got that in the wrong spot. Okay, that's better. Now it dawns on me that when this input is left to float, it appears that I'm incrementing, but I'm probably not. You know, I am incrementing, I am getting a clock cycle here, which is correct, which means I am getting a clock cycle up here when this is for the latch. What I need to do is I need to get myself a switch. All right, let's drop that right here for now. It's an active low signal, so I'm going to pull it up with a 10,000 ohm resistor. I will take its output and send that over here to this spot. And then this side will be low, so when I push the button, I get a reset. So that's good. That means that over here on pin 2, I'm seeing that. Pin 5 being resetting output, I'm seeing that. My copying latch, that's low, so I'm not copying. When I push the button, I'm setting it to be high so that I am copying. When I release it, it goes back low. All right, so the first thing to troubleshoot is the fact that I've got something incorrect with my QC latch, where the bit 5, this one, turn power off again, so that pin 5 here really should be coming from the carry out off of this IC. Let's... Okay, that's much more like what I would expect to see. Now, I should be seeing increments here, and I'm not. I should see increments there, and I'm not. Okay, so I'm counting. I'm counting slowly, but I am counting. But I'm not getting a carry signal off of here. It's simply remaining high. Whoop, did I see a flash? That's supposed to be the most significant bit, and that is oscillating rather quickly, but it is oscillating. Okay, that should be twice as fast. That should be twice as fast still, and twice as fast still. That's correct. Could it be that it is actually working, and I just don't have the equipment to be able to determine that it's actually working? My load value is not right. I did the wrong thing here. So I was fine with the clears, but I pulled the wrong signals. That makes a lot of sense. I don't know how to count to 15. Alright, let's try that again. Alright, let's try this. Let me get my clock in here, and we'll give that a shot. Alright, pull the oscillator out. I will add a hookup wire. Reset. That's working. Except it didn't count all the way through. Let's turn this off. I need to see... This is tied low, and it's tied low because it's not used, but I do believe I actually need to have visibility to it so I can see what's going on here. This is going to come over from here. D pin 9 is supposed to be low, not high on low. There it is. Okay, that's enough of that. Let's pull this back out. Turn the power back off. I'll put the oscillator back in. Power back on. Reset. That is what I was expecting to see. Now, I've got some cleanup to do here in order to make sure that I get things working properly, but it is actually counting and performing the reset. So my signals down in here related to the initial value on my counters, for whatever reason, I managed to get those all messed up. But this is working. Now, I may have to divide this clock down because, quite frankly, that may be too fast for the ROM or the RAM or both. All right, well, that looks mostly successful, and I very quickly declared victory. There are still some issues here that need to be addressed. First of all, there's still a light on the most significant bit of the address. I need to get to the bottom of that. I also need to clean up the temporary hookup wires I put in place for the debugging of the hardware. Those need to be replaced with something more permanent. I want to add back the control LEDs so that those are in place and I can use those for continued debugging. And then I need to create a ROM module and figure out how to properly test all of that. I need to make sure that all of the data is actually accurate. Finally, I might be at my limit of clock speed or might even be beyond it, but I do want to give the 10 megahertz crystal a shot again and see how well that works. So look forward to that in the next video. We'll see you soon.